Okay, what we're going to look at today is our beginning of how we're going to deal with solving other polynomial equations besides linear and quadratic equations. Okay, we already have excellent methods to deal with solving linear equations. Okay, we have several methods to deal with quadratic equations, okay, including factoring and quadratic formula. Okay, so far we've been able to solve some cubic equations and some quartic equations. Okay, but ultimately it would be nice if we had some methods that we could solve any polynomial equation. Okay. Now, to preface that, though, there are going to be some polynomial equations that we're just straight up not going to be able to solve with algebra. Okay, but there are a lot that we can if we use this idea of division. All right, so this is we call it the division algorithm for polynomials here, and this looks rather complicated. Okay, I'm going to hopefully be able to simplify it for you though as we go. Okay, so with that said, we're going to look at f of x and d of x are going to be polynomials for us. Okay, with the degree of f being greater than or equal to the degree of d. Okay, the d polynomial can't be 0. Keep that in mind. Okay, then what it boils down to is there are unique polynomials q and r called the quotient remainder such that f of x is equal to d times q plus r. Okay, and it says where either the r of x is equal to 0, okay, or the degree of r is less than the degree of d. Now that seems complicated, but like I said, I'm going to try to hopefully simplify that information for you. We're going to start though with doing the same thing except with numbers instead of polynomials. Okay? So I'm going to take a number like, say, 56. Okay? So if I take 56 and I have that be like my f, and then I'm going to let my d be 8, let's say, okay, then we should be able to write a sentence that looks exactly the same as what we have here, okay, except with numbers instead of polynomials. Okay? So I want my f on the left side, okay, and this is ultimately essentially the definition of division, if you will. Okay? So we're going to have our d function, which is 8, times something, and that something is what we're going to find, okay, and then plus something. Okay, and we should be able to write a true sentence, and we should be able to fill in these blanks. Okay, so knowing what we know about our multiplication tables, what number could we put in here that would get us the closest to 56? Yeah. In fact, this one gives me 56, doesn't it? So therefore, this would be what my r function here would be 0. So in this particular case, since 8 divides 56 evenly, the remainder is 0, which we know. True? So really what we're doing here by doing this is we're taking the 8 and we're dividing it into the 56, aren't we? Okay. Now if we did that differently, if we did numbers like 75 and let's say 4 for my f and my d, if you will, then I'm going to write down 75 equals 4 times blank plus blank. And this time 4 does not go into 75 evenly, so therefore we need to figure out how many times does it go in there. What's the closest we can get to 75? Well, we could get to 72. 72 would be 18 times 4. And then how many would be left over? 3. And so remember, though, that what we're writing here is a true sentence, isn't it? Doesn't 75 equal 4 times 18 plus 3? Sure. Okay, and so think about that from a backward standpoint, or forwards, like we're normally used to. If we were to do, like, say, 84 divided by, let's say, 6, for instance. If we were to divide those two, 6 would go into 8 once. We'd multiply and subtract. Okay? And then we would bring down our 4. And 6 times 4 is 24. We'd get 24. We'd get a 0 remainder. So in this particular case, we have a number that goes into 84. We wind up with a quotient of 14 and a remainder of 0. And if we wrote a sentence that was in this form right here, okay, our sentence would read 84 equals 6 times 14 plus 0. True? So ultimately, we're going to do exactly the same thing we're doing right here with numbers, but we're going to do it with polynomials. We're going to be given an f, if you will. We're going to divide it by d, and we're going to get a quotient and a remainder. So nothing different than what we just did right here. Now, is the algebra going to be more difficult? Yeah, because we're going to be dealing with polynomials instead of numbers. Okay, but with that said, let's go ahead and take a look at an example of what we're going to actually do with this. Okay, how do we do this polynomial long division, we're going to call it. Okay, because the bottom line is what we want to figure out then is this. I'm going to give you kind of what the end result is going to be when we get this done. Okay, we're going to take this and we're going to divide it by this. Okay, so we'll get to the algebra of that in a minute. But I want you to think about why we would want to do this. Okay, what did I just figure out then? If I divide 84 by 6 and I get an answer that has no remainder, what does that tell me about the 14 and the 6? What are they to 84? If they divided evenly, we call those what? If I said that, I'd say 6 is a what of 84? It's a factor. Okay? 14 is also a factor. So by finding that I get a 0 remainder when I do the division, I'm finding factors. True? So think about what we're going to ultimately do with this. And it's, in general, we don't know how to do anything with a quartic function in general. But if we could find a factor, that would help us solve an equation that this was in. True? Because ultimately, like a quadratic equation, we'd want to break this down into its factors if we were trying to solve it, set it equal to 0 and solve it. True? So that's essentially what we want to do. We want to divide these two because if this turns out to be a factor of that, okay, then we can break it down into simpler equations. Okay, just like we did with the quadratic equation earlier. If we could break this quartic into two quadratics, okay, we know how to solve all quadratics. True? So wouldn't that be good? That would get us to our goal, because our goal eventually is going to be to solve this equation. All right. So we're going to look at, like I said, this idea of polynomial long division. I want you to follow this very closely. We're going to divide x squared plus x plus 1 into 2x to the 4th plus x cubed minus 3. And we're going to get a quotient and a remainder. And again, if we're lucky, the remainder will be 0. Okay? If we're not lucky, then we'll just get an answer here, and we'll just have to settle for the fact that it has a remainder to it, and that it's not a factor. Okay? If the remainder is 0, it's a factor. And what's most powerful is not only is this a factor if we find a 0 remainder, but wouldn't the quotient also be a factor as well? Okay. So let's find out if it is in this case. So here's the procedure what you need to work on. Okay, we're going to always focus on the leading term. Okay. And we're going to ask ourselves, if I look at the leading term here and the leading term here, okay, what can I multiply this leading term by to get to this leading term? 2x squared. Okay, 2x squared is going to be that part. Because again, if I multiplied this by just 2, I'd have 2x squared, but I need 2x to the 4th. True? So I'm going to multiply, I'm going to decide what is it going to take for me to get to this, from this to this with multiplication, and I'd multiply by 2x squared. Now, step 2, after you figure that out, is you're going to take that, whatever you found here, and you're going to multiply it by the entire trinomial here, or binomial, or whatever it is out here. Okay? So I'm going to get 2x to the 2nd times x to the 2nd. That's going to give me 2x to the 4th. Then I'm going to go 2x times x to the 1, which is 2x cubed. And then I'm going to go 2x squared times 1, which is going to give me 2x. Okay. All right. Now, before we continue with that, I'm going to show you a technique that I would probably choose in this case, just to make my division part easier for myself. Okay. When I do this, I would write x squared plus x plus 1, and then as long as all the terms were present here, that's good. But when this one, we notice that we don't have a squared term and we don't have an x term here, do we? Okay. So I would write it as 2x to the 4th plus x cubed plus 0x squared plus 0x minus 3. Okay. So I would put those missing terms in there because it's going to help us for the subtraction part. So if I have 2x squared, then I'm going to write it as 2x to the 4th plus 2x cubed plus, oops, this is supposed to be squared, sorry, 2x squared. Okay. Alright, so when I multiply the 2x squared that I got by each of these three, I'm going to wind up with that. Okay, like I said, I would probably do it like this. That way, if you do that, if you put in the missing terms, then you're going to have everything line up real nicely. Because right now, notice these line up, but do these line up? These are not like terms, are they? Okay, so like I said, I would add those missing terms in there just because it's going to be easier for you to do the next step, which, just like in any division problem, is to subtract. Now, the other piece of advice I would give you on the subtraction part here is put this in parentheses. Okay, remember we're subtracting all three parts in this case from what we have above. Okay, so if we do that, 2x to the fourth minus 2x to the fourth is going to be 0. Okay, which is good. That's the whole reason why we chose 2x squared. Okay. And then when we do these two, we're going to have x cubed minus 2x cubed. That's going to be negative x cubed. And then I'm going to have 0 minus 2. That's going to be minus 2x squared. And just like any other division problem, I'm going to bring down my 0x. Okay. And then I'm going to start the process over again. Okay. You could bring down the 3 if you want to. You don't necessarily have to bring down 2 parts at a time. You could if you wanted to. Eventually we're going to bring the 3 down, but you don't really have to do it right now. Okay. Although it's not going to hurt to have it there. So if you want to bring down the whole thing, that's cool, because we're just going to line up parts anyway when we do the next step. Okay. So now again we start over. So we go back to our leading term. Okay. Here's our 2 leading terms right here. What can I multiply this one by to get to this one? Yeah, negative x would do it, wouldn't it? Got to make it negative, and I got to have another x here, so it'd be minus x we put on top in that next column. And then if I multiplied the negative x times this whole entire thing, I'd get negative x cubed minus x squared minus x. And then I'd put parentheses around that and subtract. And here's where you got to be careful with the subtraction part, and this is where people generally mess this up, is because we screw up the subtraction part with the signs. Okay. So when I do these two, negative x cubed minus negative x cubed, that's really plus, so those are going to be gone, and that's good. That's what we want to have happen. But when we do this one, we're going to have negative 2x cubed minus minus again, so it's really negative 2x squared, I should say, plus x squared, so we get negative x squared. And then 0 minus minus really means 0 plus, and so we're going to have that as our remainder, or our subtraction part. All right. Now, if we can keep going, we will. And we can always keep going as long as the power on our leading term is either the same or bigger than the leading term power here. So ultimately, the only thing I got to do now next is multiply this by what to get this? If I multiply x squared by negative 1, I'd get negative x squared. So we're going to go minus 1. So it'd be negative x squared minus x minus 1. Parentheses, subtract, and it's going to wipe these two out. Okay, but when I do this one, it's going to be x minus minus, really means x plus. So we're going to get 2x, and then negative 3 minus minus 1 is going to be negative 2. And then we got to ask ourselves, can we keep going, or are we done? We're done. Okay, because once we get to the situation where the subtracted part, okay, has a degree of less than the divisor, okay, then we're done. And that right there becomes our what? Our remainder. Okay, so before we actually finish the answer to this and talk about how to present it, let's go back to, let's say, 68 divided by 5. Okay, and see that this is really exactly the same process. We need to ask ourselves again, how many times does 5 go into 6? It'd be 1. We subtract and get 1, bring down our 8. 5 times 3 would get us to 15. And once we get to 3, and we're out of digits here, 5 does not go into 3, so that 3 becomes our what? Our remainder. So one thing we learned is that we could write it as 13 remainder 3, final answer. Okay, but more importantly, and what we're going to use here is the other way we learned it, which is the answer is 13, and then 3 over 5. And again, that structure is always remainder over divisor. Okay, if we were to divide 68 by 5, we'd get 13 and 3/5. Okay, always remainder over divisor. So if I had to present the answer to this, I would say that it's the quotient. This was the 13 part. So our quotient is 2x squared minus x minus 1. Okay, and then plus, because when we say 13 and 3/5, that's the same as 13 plus 3/5. So we would do the same thing here with polynomials. We'd write the quotient plus the remainder, which is 2x minus 2, over the divisor, which is x squared plus x plus 1. And that right there would be the final answer. Okay. Now, one thing that is unfortunate for us in this case is we didn't get a zero remainder, which means that this is not a factor of this. So that kind of stinks, huh? Would have been nice if it were, because then we would find factors, we'd be able to break that down in an easier manner. Fair enough? Okay. But ultimately, in this case, it wasn't. So the answer to the question, we can certainly answer it. Okay. It really doesn't do any good to us in terms of finding solutions to an equation because it's not a factor. Okay. If it were a factor, then it would help us, and we'll talk about that very soon.